Hello children. Real simple, real straightforward lesson today. First we're going to do this problem. As you know, it's neither momentum is conserved in the beginning and energy conserved at the end. So last unit we talked a lot about the pendulum, and we were basically hinting at this idea. We have to use radians a lot in physics. It worked out because of some weird approximation we did last semester or last unit, but now we're going to use radians again more exclusively, and it's going to be really useful. Degrees are okay because you're used to them, but they really don't really make a lot of sense. They're based on dividing up a year into 365 days, and that's rounding 360. It is a nice round number, easy to divide up into 4 or 6 parts or whatever, but radians will be a lot more useful. Hopefully you guys remember the definition of a radian. If you have a circle of radius r, this distance right here, the arc length, is called s. And a very nice, straightforward calculation, theta, the angle here, in radians is s over r. If s is in meters and r is in meters, theta actually has no units. So sometimes I'll call an angle in radians, I'll say the number of radians, but sometimes I'll just skip units and say, oh, it's this much, because we're going to use angles in radians a lot. And I will say radians to remind you guys, but radian is not really a unit. It's actually a ratio, length for length. It's really no units, which is nice. It makes some things better, so it's good. Don't worry about that. Not much else to say, other than, hey, remember radians? I hope so. We're going to call theta, not the angle. We're going to call it angular displacement. I could have used the word rotational displacement or even angular rotational. There's one other word, angular rotational. It doesn't matter. I'll use a bunch of different words for this, but notice it's displacement, which we talked about a lot, plus angular. So it's an angular analog or an angular version of displacement. So yeah, pretty straightforward. This is really useful, and it's much better than degrees for this idea. Imagine this circle is a wheel, and the wheel is rotating. Imagine just the marker is rolling across my hand, or a ball is rolling across the ground, or anything. The displacement d that the ball travels, it actually is s. If my marker rolls 10 centimeters, then the little part on the bottom touching the ground actually moves basically across a circle 10 centimeters. In real life, the distance isn't quite the same, or the displacement is not quite the same, because it's going in circles. But if it makes a full circle and ends up back on the ground, they would be the same. And if we ignore the up and down motion of the circle, which we will, I don't want to confuse you guys, they are the same. They are the same. If a wheel rolls 5 meters, around the circle, each part of the wheel went 5 meters around. And if you wanted, you can define the angular displacement of each part of the wheel from this formula, r theta. So G is r theta. Here's a big idea we'll see all throughout this unit. Displacement is r times angular displacement, or rotational displacement. Um, we'll see how the linear and the angular are related all throughout this unit, all the time. That's great. Yeah. So this does work if you were ever in a car and there's like a little dial on the car, not the speedometer, it's called the odometer. It's how far the car is driven in its whole like lifetime. That's not based on GPS data or anything weird like that. That just records how many times the axle of the car turns and multiplies by the circumference of the car's tires and says, oh, well, the car's tires have rotated a distance of 100,000 miles. That means my car has also traveled 100,000 miles. And that's based on this formula, D equals S R theta. They know the radius of the car's wheels and multiply it by theta to find D, the displacement of the car, or distance of the car. Cool. Not much else to say about that. One important thing, clockwise is negative and counterclockwise is positive. Same as pre-calc, I believe. Clockwise, counterclockwise, positive. I don't know if it's helpful for you, probably not, but if you need a shortcut to around it, just take your hand and just like plop them down on your paper or your whiteboard or whatever with 2 thumbs up because you're so awesome at physics. The right way to measure rotation is on your right hand. The fingers of your right hand go in the positive direction, counterclockwise. The fingers of your left hand go clockwise, the negative direction. So the right way to measure angular displacement is the fingers of your right hand. Yeah, great. Don't confuse yourself taking a test with your right hand and you don't want to put your pen down, use your left hand. It's the right fingers of the right hand. They rotate counterclockwise around your thumb. If you look down at your thumb, like so. So pretty straightforward. Displacement or theta, angular displacement. Even though like as something rotates, we might say, oh, it rotates around the circle. It was displaced nowhere. We don't really say that. I know that's true. You probably remember. Oh, I know. Someone's going to trick me with the displacement versus distance. I'm actually not really going to trick you with displacement versus distance. Technically, it's true, but angular displacement basically will say it's 0, pi over 2, pi, 3 pi over 2, 2 pi. We would say this is a displacement of 2 pi. So if a wheel rolls one full rotation, its angular displacement was 2 pi or 2 pi radians. If a ball is thrown in the air and it makes one full flip, we'll say, oh, it was displaced at an angle of 2 pi radians, even if every piece of the ball ends up in the same place. You might say, oh, the displacement's 0, but we'll still say the angular displacement is 2 pi. This is only for rolling objects, rolling across a flat level ground. Rolling. So don't worry, I'm not going to trick you guys too much with displacement and angular displacement. We're just going to focus on the angular or rotational for basically the whole unit. Pretty cool. We can do one last thing really fast. What's the formula for the area of a circle? And how do you know? Where does it come from? Where does this formula come from? What's the formula for an area of a circle? Where did it come from? Any ideas? Here, imagine this is like a roll of paper, like toilet paper, except solid all the way through the middle. Imagine I took all these rolls of paper and I chopped them and just cut from the top down to the middle. All the pieces of paper would kind of just like fall open, right? How long would the first layer of paper be? How long would the first layer be? it would be the circumference of the circle. Then the next layer would fold open. It would be slightly shorter because it's a slightly smaller circle. And the next layer, every layer of paper will be a slightly shorter piece of paper because it's a slightly smaller circle. So if you stack them all up, you'll eventually get this triangle, this pyramid. What's the length of the smallest piece of paper? Well, it's effectively 0, because as the radius becomes 0, you get basically no paper. So we get this triangle of paper, which is the same as this circle, just rearranged, with base 2 pi r, and height. This is the bottom of the first piece of paper. This is the bottom of the last piece of paper. Height r, oh my gosh. The area of a circle is 1/2 base times height. It's 1/2 2 pi r squared. It's 1 pi r squared. Okay, cool. Okay, sorry. I forgot one last thing we gotta go over. That was not really important. But I already did it, so enjoy. Whenever we're talking about rotation, which we are this whole unit, in case it wasn't clear, we need an axis of rotation. For a circle or a wheel or a ball, it's pretty obvious. It's right in the center. You can say it's where r equals 0 meters. That's fine. We're going to see things rotating that are not perfect circles. So a lot of times you'll see, oh, instead of a ball rotating, it's a stick, or a rod, or a long, thin rectangle. Okay. Where is the axis of rotation for a long, thin stick or rectangle? Where would you put it? What do you think? It was a trick question. There is no set answer. You can put the center of the object as the axis of rotation. That's fine. That's good if the object rotates around the center, like so. Maybe like a seesaw. At the playground, a seesaw is held in the middle and it goes back and forth like that. For a seesaw, the axis of rotation is in the center. But what if you are swinging like a sword or something weird? That's what swords look like, apparently. I didn't know either, but that's what happens. If you're swinging a sword, you're not going to hold the center. You're holding the end, the handle, the palm, the hilt, whatever. And the whole thing swings like this. So for a sword, the axis of rotation is on the end, and that's fine too. All that matters is the axis of rotation is where you say r equals 0. So for some objects, depending on the object, you gotta read the problem. If it swings around a fixed end, that's the axis of rotation. If it swings around a fixed center, that's the axis of rotation. It doesn't really matter where, as long as r equals 0. It could be in some random place in the middle. No one knows for sure. But that's a quick, easy intro into rotation. And if you're really smart, you can probably guess what our next assessment is going to be, or at least like the second half. I'll see you guys in